Hello everyone. In this video I will be discussing the SN1 mechanism for nucleophilic substitution reactions. Quick notes and reminders regarding this mechanism would be that this mechanism dominates in tertiary halogenoalkanes. It involves the formation of a carbocation intermediate. It is a two-step mechanism and is non-stereospecific. An example of this reaction would be the reaction of 2-iodo-2-methylpropane, which is a tertiary halogenoalkane, because the carbon atom bonded to the halogen is bonded to three methyl groups, three alkyl groups. We will discuss its reaction with NaOH or KOH, so that's sodium hydroxide or potassium hydroxide, and the students once again should be able to identify that the hydroxide ion is the nucleophile that would displace the halogen. The reaction once again is a simple substitution reaction in which the hydroxide ion will displace the iodine atom to form an alcohol. The mechanism, however, is not as simple. The mechanism, as stated previously, involves two steps. Step 1 is the rate determining step, the slow step, which involves the formation of the unstable carbocation intermediate. If we have a look at the molecule of 2-iodo-2-methylpropane and focus on the carbon atom bonded to the halogen, the iodine atom, with a partially positive charge, we would notice that in this case it's surrounded by four bulky groups, three methyl groups and one large iodine atom. Thus, the steric hindrance is somewhat high here, and there's no way for the nucleophile, which in this case is the hydroxide ion, to approach the partially positive carbon due to high crowding or high repulsive forces. Thus, the halogenoalkane would undergo heterolytic fission, in which the iodine atom would break heterolytically, taking both its own electron, color-coded in red here, and the carbon's electron color-coded in blue here, forming a negatively charged ion, and a carbocation an intermediate in which the carbon ion here has a formally positive charge, which is unstable. In terms of the stability of carbocation ions, I will discuss in videos to come the stability of carbocations, but to state it simply in this video, I would state you should know that alkyl groups have very low electronegatividity values, such as carbon and hydrogen atoms, and thus do not hold very strongly onto their electrons. Thus, a species with high electronegatividity or a formally positive charge can very easily attract their electrons more towards them to stabilize their positive charge, and thus spread the positive charge over more than one nuclei. Thus, this would become less positive, this would become a bit positive, a bit positive, and a bit positive, which forms a more stable carbocation. Thus, this is a tertiary carbocation because it's surrounded by three alkyl groups. The carbon with a positive charge is surrounded by three alkyl groups. If this were a secondary carbocation, it would only be bonded to two alkyl groups, and thus the stabilization of the carbocation would be less. And also, if it were a primary carbocation in which this carbon was only bonded to one alkyl group, the stabilization would be even less of the positive charge on this carbon atom. In this case, this is the most stable type of carbocation intermediate, although all carbocations are considered unstable, but this is the most stable one. Still, the formation of a tertiary carbocation requires somewhat high activation energy, and thus at a specific temperature this would be the slow step because it requires a lot of energy to be formed. One should also note the geometry of this carbocation intermediate, not only because it is usually tested, but to explain why this reaction is a non-stereospecific reaction. This carbon with a positive charge, the central carbon atom with a positive charge, is surrounded by three bonding electron domains, thus forming a trigonal planar geometry with 120-degree angles. And thus the structure is now a planar structure in which the carbon with the positive charge is exposed from the top part of the plane and the bottom part of the plane, which makes it easier for a nucleophile to approach this carbon with a positive charge and donate its pair of electrons in the second step, which would be the fast step, since it forms a more stable compound in which the carbon has 8 valence electrons. This step has a lower activation energy and thus would be the fast step. As you can see here, the carbon with the positive charge, the nucleophile donates its pair of electrons to form the alcohol. I'm going to read the notes I wrote. This is once again discussing this central carbon atom with the positive charge. This should be a formally positive charge. The carbon with, actually the carbocation, this is actually a partially positive charge because I'm still discussing this part here. This central carbon, when it's bonded to the iodine and 3 alkyl groups, has high steric hindrance, which we called crowding, because it's bonded to 4 bulky groups and thus cannot accommodate a 5th group, which in this case is the nucleophile. Therefore, as I previously stated, it undergoes heterolytic fission to form a tertiary carbocation intermediate stabilized by 3 positive inductive effects. The rate equation would translate into the rate equaling the rate constant multiplied by the concentration of the halogenoalkane to the order of 1 with respect to the reaction, since the slow rate determining step is unimolecular and only involves the halogenoalkane appearing once, imparting this mechanism with an overall order of 1, such as SN1. Its molecularity. The mechanism is favored in this case by the formation by using polar protic solvent. As stated previously, an SN2 mechanism would be favored by using polar aprotic solvent. This mechanism is favored using polar protic solvent. I will be posting another video regarding the choice of solvent to explain their effects on increasing or decreasing the rates of an SN1 mechanism or an SN2 mechanism. As I stated previously, it was also worth mentioning that the carbocation in this case has a planar structure, so we can explain the inversion of configuration if this were a chiral carbon, which in this case it isn't. Since it has the carbocation intermediate formed in step 1 will react with the nucleophile in step 2, but now there's a 50-50% chance of the nucleophile approaching the carbocation from the top of the plane or the bottom of the plane. If it approaches from the top of the plane, it would invert or repel these bonds downwards, thus the inversion would be downwards. If the approach was from the bottom side of the plane, then it would repel these bonds upwards and invert these bonds with the methyl group upwards. In this case, this is not a chiral carbon, and both these molecules are identical, which is 2-methylpropan-2-ol. But if this carbon were a chiral atom, these two molecules would differ in configuration and would form 2 different enantiomers. 50% of this optical isomer, the enantiomer, and this 50% of the other optical enantiomer. Enantiomers are non-superimposable mirror image molecules. This is why, in this case, we do not need to draw the mechanism as a 3D or using stereochemical formulas, because it is a non-stereospecific mechanism, because it's a two-sided approach of the nucleophile, and thus it's a two-sided inversion occurs, and both enantiomers would form equally if this were a secondary carbocation. And thus the mechanism as seen above here is drawn using simple Lewis structures. It should be also noted, at this point when I teach in a classroom, students would come up to me and ask me, why doesn't an SN1, an SN2 mechanism undergo heterolytic fission heterolytic fission instead of forming a transition state. If we were to go back to that video and look at the molecule in that case, that molecule is a primary halogenoalkane. If heterolytic fission were to occur, the carbocation intermediate that forms would be a primary carbocation intermediate stabilized by one positive inductive effect, which is fairly the lowest, the least stable carbocation and has the highest activation energy, and thus since it can accommodate a fifth group in that case, because it's not bonded to four bulky groups, the mechanism proceeds via a one-step mechanism with the formation of a transition state. Therefore, if in an exam a student is asked to explain why halogenoalkanes undergoes SN1 or SN2, a student should mention steric hindrance as well as the stability of the carbocation that would form if it were to go heterolytic fission. Thus, for SN2 mechanisms in the previous video, they have low steric hindrance and thus can accommodate a fifth group, which is the nucleophile. But if it were to undergo heterolytic fission to break off the leaving group, which is the halogen, it would form a primary carbocation intermediate, which is the less stable intermediate because it's stabilized by one positive inductive effect. On the other hand, an SN2 mechanism, an SN1 mechanism, which dominates in tertiary halogenoalkanes, it has the central carbon bonded to the halogen has high steric hindrance because it's bonded to four bulky groups and thus cannot accommodate a fifth group. But when it undergoes heterolytic fission, it forms a fairly somewhat stable carbocation in comparison to a primary or a secondary carbocation, which is stabilized by three positive inductive effects. That would probably cover everything required from SN1 and SN2 mechanisms. I will be posting part 4 soon, which will cover a secondary halogenoalkane which undergoes both SN1 and SN2 mechanism, and I will draw both mechanisms and discuss the enantiomers that would form, since that the central carbon bonded to the halogen would be a chiral carbon. And I would give an example of how an SN2 mechanism produces only one of the enantiomers, since it's a one-sided approach of the nucleophile, while an SN1 produces 50% of each enantiomer, since it's a two-sided approach of the nucleophile. Thank you for watching.